so here's another example. So you know what composition of functions is, like f of g of 7? So this is a function that does composition of functions. It creates the composition of two functions f and g, namely lambda of x, f of g of x. Okay, so compose first but first of right, so compose first but first is the function that takes the second letter of a word or the second word of a sentence, because it's lambda of x, first of but, first of x. So this is, I think, really incredibly cool that with compose, when I said compose first but first, there's nothing about the argument in there, right? It's just entirely at the level of functions that we're manipulating things. So define twice f to be compose f with itself. All right, so let's do twice square root of 16. Oops, too many close parentheses, right? You are. But twice square root of 16 is 2. So twice square root means the square root of 16. Twice but first. Okay? So it's but first of but first. So if you get accustomed to working with tools like this, you can very, very quickly build up interesting functions that do something you want to do. Anybody here programmed in Pascal ever? Is it like one person? Okay. It's kind of a dead language. Pascal is interesting because it does 1, 2, 4, but not 3 for procedures. Procedures, not just pointers to procedures, but procedures can be passive variables, arguments, members of data, but they can't be return values. And again, that has to do with this cost question. That's the thing that's expensive. So that's kind of interesting that they left that out. They knew what they were doing. You can tell that they knew what they were doing because they built in the data type and it does almost everything, and they explicitly say this is an exception. Okay, so here's a function that takes a quadratic equation, the coefficients of a quadratic equation, ax squared plus bx plus c equals 0, and solves for x. And as you remember, quadratic equations have two solutions, right? Minus x plus the square root of blah, 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 and minus b plus the square root of blah, 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 and minus b minus the square root of blah, 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 each of them over 2a. So what we're going to return, since a function can't return two different values, we're going to return a sentence of length 2 containing the two values. So if I say, let's pick an easy example. Oops, yeah, 1. Does this work? Yeah. Right. Okay. So we get a sentence with two numbers in it. How does that work? Well, it's totally straightforward. Here's sentence. Here's minus b plus the square root plus the square root of b squared minus 4ac over 2a. And here's minus b minus the square root b squared minus 4ac over 2a. Right now, this is pretty ugly and a little slower than necessary. These days, it wouldn't be worth really making this kind of optimization in terms of computer time, because computers are so fast. But I remember back when taking the square root of a number was something that if you were doing it to a lot of numbers, you would notice the time of. And if we could do it once instead of twice, that would be great. So what we would like to do is take that value, square root of b squared minus 4ac, compute it once, give it a name, and use that in constructing the two solutions. Well, we have a mechanism for computing some value and giving it a name, namely procedure calling. Right? So what a formal parameter does in a procedure definition is it gives a name for some argument that you're going to give when you call it. So here's my new version. And it still works. And the way that it works here I define a helper procedure called roots1 that has a formal parameter d for discriminant. It's an internal definition because we're only using it inside of roots. And here's the body of roots where we call it. We call roots1, and the actual argument expression is square root of b squared minus 4ac. So the actual argument value is, the square root of 25 minus 24. So d would be 1 for that particular equation. And then up here, in the body of roots1, here's where we have the plus and the minus combined together. And we can just use d instead of computing it twice. So this is a little bit faster and a lot less code to read. So maybe a little bit clearer. But I don't really like having to define a helper procedure roots1. That seems a little awkward and clunky. Well, since I'm only using it once, I don't have to define it and give it a name. Instead, I can do this. Notice, by the way, where the cursor is, there's two open parentheses next to each other. This is not anything special like a con clause, where those have a special meaning. This is just two procedure calls, one inside the other, except the inner one isn't actually a procedure call. It's a special form, namely lambda. Lambda creates a procedure, and then the outer parentheses invoke that procedure with this actual argument expression. Okay? So this is how, in Scheme, given the ability to define and create and call procedures, we can make up names for intermediate values that we need in the course of a computation. So we only have to compute them once instead of a bunch of times.